Thanks for the invitation. This is a great opportunity for me to speak here. It's my first time to visit this part of the world. But anyway, I enjoy it very much. This is actually joint work with Bao Mingdeng and Chang Fu. Bao Ming is a faculty member of the Beijing Normal University, and Chang Fu is from Tongji University in Shanghai. And I'm visiting ECNU just recently, so I said via East China Normal University. So, what is quantum Schur-Weyl theory, first of all? So, I want to just clarify a little bit. It investigates 3 levels of theoretic relations. So I just try to explain a little bit more, Of course, quantum Schur-Weyl theory, that's Arun mentioned and other people mentioned too in this conference. And, normally it's called the Schur-Weyl theory. So it includes the second part, certain category equivalences. So that's between the category of Hecke algebra modules and the quantum Schur algebra modules. So usually we talk about sort of a going up approach. You look at the representation of Hecke algebras, then you try to see what happened for the representation of Q-Schur algebras, quantum Schur algebra, then the quantum GRN, etc. Now I would like to add to this theoretical relations, the last part of the theoretical relations, I said, realizations and the presentations. So what does that mean? The quantum GRN is defined by generators and relations. And the quantum Schur algebra is defined by certain endomorphism algebras. So the realization problem, like the Ringel-Hall algebra realization for the positive part of quantum groups, the realization problem for quantum groups is to reconstruct them as vector spaces with certain explicit multiplication on elements of basis. So this is what I mean, compare with the Hall algebra realization for the positive part. And the presentation, well, of course, from the connection between quantum GRN and the quantum Q-Schur algebras, it is natural to ask for a presentation, the generators in relation for quantum Schur algebra. So that's kind of a pair of relations, it's around. So for example, the quantum GRN realization, that's beautiful Bailins and Ludwig McPherson's work, which reconstructed the quantum GRN through quantum Schur algebras. And we can mention, the realizations, Dote Giacinto, attempted to get the presentation for quantum Schur algebras, and we also did some work around this line, etc. Now, this part of the theory, quantum Schur-Weyl theory, can be found in this recent book. So about 40% of the book is talking about this part of the theory. But anyway, it's just 40%. My question is there sort of affine quantum Schur-Weyl theory around? Well, you can say quite a few about this question. For example, in 1993, Ginsburg, Vasserot has sort of a geometric construction for the affine quantum Schur algebras. And in their paper, they also mentioned the connections between quantum affine SRN and affine quantum Schur algebras. And 1999, Richard Green defined, affine Q-Schur algebras through Hecke algebras. Now, of course, affine Hecke algebras of type A. Then the same year, Lustig actually published a paper, point out, a sort of a mistake in this paper, which claims the quantum affine SRN maps onto quantum Schur algebra. Now, Lustig gave an counterexample and said, no, this is not the case. Then, okay, let me try to mention another important paper that's Vernuro and Veserod's paper on tensor space and on bimodules, bimodule structure, by Hall algebras and affine Hecke algebras. And these are relatively earlier papers. And you can find a long list of other papers like Olivier Schiffman, Andrew Hilbrey, Kevin McGurty, Doty Green, etc. They are all talking about quantum affine GAN, presentation of quantum affine Schur algebras, etc. So because of this counterexample, that makes me so puzzled for you as well, because the presentation in this paper for quantum SRN is quite different from the presentation given in this paper. So at some point, I don't know if the two quantum groups are actually the same. Because if they are the same, yes, it's a counterexample. If they are not the same, I don't know what's wrong with that. But anyway, that's some question in my mind for some years. But anyway, we tried to approach this question now. We find some ways. But anyway, so let me mention the quantum affine GAN, the versions. First of all, Lustig has a version. This is maybe should not be called quantum affine GAN. So I said it's an extended quantum affine SRN because you have the quantum affine SRN, then you extended the zero part by an extra generators. So then you will get the Lustig so-called quantum affine GRN. But that's quite different from the Drinfield's quantum affine GRN. Now this is so-called new presentation or new realization. But in that presentation without using Chevrolet type generators. So it's quite complicated, involving infinitely many generators and quite complicated relations, etc. There's another version called the R matrix version by these two guys. And so the last two versions actually are relatively complicated, involving coefficients of certain formal power series, and of course, but they have nice properties into the representation theory, and a nice application. But they're not convenient for defining an action on the tensor space. So that's a question, Find the Drinfield Jimbo type presentation for quantum affine GRN. I don't need this hat here. Yeah, that's right. So, candidate, double linear Hall algebras associated with the secret quavers. So this is our starting point, built on Schiffman, Hilbrey, and Vivi's work. And so let me start with this definition. So I started with the secret quavers. You see, that's a secret quaver, right? All errors are in the cyclic direction, the same direction. And now I take the linear Hall algebras over the Laurent polynomial ring of integer coefficients. So I'm not going to define the details. So it's a Hall algebra defined over there. The basis are isomorphism classes of nilpotent representation of the cyclic quaver. And then I extended the linear Hall algebra by adding the zero part to it. Okay? So this is like the Borel part, greater than or equal to 0 and less than or equal to 0. But over these two algebras, you can introduce Green's co-multiplication to get the bi-algebra structure, and introduce J-Shell's antipode to get Hopf algebra. So you have a pair of Hopf algebras. Then there is a so-called skew-Hopf pairing, which is used by Drinfield to construct the Drinfield doubles. So you can explicitly write down such a skew-Hopf pairing, and that gives the so-called Drinfield double. So it's kind of you take the tensor product of these two Hopf algebras, then the skew-Hopf pairing gives you the multiplication, the commutator formulas. Okay, so that's where we need the skew-Hopf pairing. I will mention that some application later on. Now, then define the double linear Hall algebra to be the quotient. Well, because you have one zero part, a copy here, and another zero part, a copy there, then you just I need one copy, so I mod this algebra by this ideal, then you get a single copy. So that's the double linear Hall algebra, and this is the definition, And what we are interested in is kind of a presentation. What are the generators? What are the relations? So that theorem, basically built on the work of Schiffmann, who first proved that the Hall algebra is isomorphic to the composition algebra. That's a positive part of quantum SRN, affine SRN. And the tensor with some polynomial ring involving infinite many indeterminate. So then Schur-Weyl, reconstructed these central elements, element in terms of modules, right? Because you are in the Hall algebra, and you have the basis of isomorphs and classes of modules. Then with this whole Schur-Weyl's explicit constructions, then you look at the Schur-Hoff pairings, look at their actions, and you can find the following presentation. So it's generated by the double linear Hall algebra, is generated by this part for the EI, FI, KI inverse. Of course, where I is varies from 1 to the n, the number of vertices of the quiver. Then you have these elements, ZS plus, ZS minus. These are so-called central elements. So the relations, so these are for the EI, AI, KI, just like that's the same algebra mentioned in Arun's talk, So this is the Lustig's quantum affine GRN, you may say. Then plus the relations, that's a central element. So they are very trivial, just commutes with everything. So this is very clear, the presentation for this double linear Hall algebra, and that's our quantum, the candidate for quantum affine GRN. So you need, hopefully, to prove this is the isomorphic to the Drinfield's one, okay? So let me remind you this Drinfield quantum loop algebra definition. So that's the loop algebra. You get the generators like infinite many generators, XIS plus minus, of course KIs, and there are some other generators, corresponding the matrix EII, tensor with the power of T. And then these are the relations. You see, look at this relation involves these elements, like the KIs, you see, are defined by certain generating functions. But it's a nice presentation, but it involves infinite many generators. And so this algebra and double linear Hall algebra should be the same. So what do we need? Well, just look at, so it's actually Bake's monomorphism convinced me. Lustig's so-called quantum GRN is the same as the Drinfield's generalization for quantum affine SRN. So Bake has the following injective half algebra morphism. This is Drinfield-Jimbau's presentation. Use EI, Chevrolet generators, EI, FI, KIs. Send into this quantum loop algebra I defined in the previous slides. Then the map is explicit. So that's sort of find the connection between the Drinfield-Jimbau's presentation with this Drinfield's new realization. And actually, the image of this map is you can explicitly describe the generators in the relations in a Drinfield presentation manner. So that's the way to do that. So when I see this, okay, that's exactly mentioned in these relations generators in Ginsburg and Verselot's paper. So they are really talking about quantum affine SRN. So therefore, at this point, Lustig's counterexample is very right. Okay, so we want to lift in Bake's monomorphism. That should not be difficult, right? Because you have already, the SRN part. Then you just lift it, to the double linear Hall algebra. So you get an algebra isomorphism, and of course, Schur-Weyl did this at the Hall algebra level. So you just lift it to the double Hall algebra level, then you can get this. So this new presentation is very useful for for example, the establishment of affine quantum Schur-Weyl theory. For example, the action of this algebra now the same, right? The same. on the tensor space, I missed the space here, becomes very easy. And also, you can, because now I have the double linear algebra, right? I have 3 minimal sets of generators for this quantum affine GRN. First, Schur-Weyl type generators that I mentioned in the first theorem. Homogeneous semi-simple generators. That's corresponding to homogeneous semi-simple modules. Homogeneous means the dimension vector corresponding to the multiple of the imaginary roots. And the homogeneous indecomposable generators. So you look at those indecomposable modules, isomorphism classes for indecomposable modules. And their dimension vectors are just the imaginary roots. Then you get 3 minimal sets of generators. Each generator, each set of generators, is convenient respective. For example, this one is nice for the action on the tensor space. And this one, the semi-simple generator, should be useful to the root type integral forms. And then you can probably get the kind of a root of 1 theory. And this one, we believe, the homogeneous indecomposable generator should be able to give us explicit multiplication formula. Then you will get the realization problem solved. So that's all about this new presentation. So let me try to convince you, first of all, how do you get to the action of quantum affine GRN on the tensor space? So let's do that. So I take an infinite dimensional free Z module, right, with basis indexed by integers. I take the vector space, corresponding vector space, as change the forms to boldface forms. Now this definition is very natural, you see. EI, FI, EH, FH, KH, that's defined as usual, you see, that's the standard definition. And how about the central element? Well, the central element, the plus part is just like a translation, omega I to omega I minus Tn. So if this is T, Zt minus, then omega I plus Tn. So here the plus is this minus, the minus is plus. So that gives you the translations. So you can check easily because we have the defining relations. So this defines natural double Hall algebra module. Okay, then it induces, because it's a half algebra, a double Hall algebra, action on this tensor space. So that's by the half algebra structure. And then you got 2 algebra homomorphism, right? First, because this is nonsense. I haven't yet defined it, so I still have some problems in my slides. But anyway, I mentioned shortly about the Heck algebra part. But anyway, you have algebra homomorphism because it's action, so you have this, right? So I want to work out the images of these 2 maps. So I will define this shortly, okay? The second map, this kind of a dual map, all right? So now, so that's, with the new presentation, you can easily construct such a natural representation on the infinite dimensional space and induce action on the tensor space. Then you should think about the image of the quantum affine GRN or the double linear Hall algebra. That's the same. So I need the Heck algebra, right? So I want to get to the action on the tensor space on the right. So this is what I'm going to do. So the affine symmetric groups and its Heck algebra. So I first quickly get to the Heck algebra. So I take the group of all permutation from integers to integers, satisfying certain periodic relations. This is called the affine symmetric group, sometimes called extended affine Y group of type A, whatever. And then you can have, the group, the relation with the affine Y group of type A, okay, or Y group of affine type A, and the symmetric group, etc. So the relationship between here, you see, this is the Y group. You need an extra condition to get the Coxeter subgroup. Then you need this translation. Then that's a semi-direct product. And this is also very important. The Y group, and this is like the lattice of weight lattice. So you have this kind of description. And then you extend the length function from the Coxeter group, here W, to the affine symmetric group. Then you can define the Hecke algebra. That's in a very standard way. So I didn't, you still have certain simple reflections from this group because this is a Coxeter group. So that's a quadratic relation. Then when length is additive, you use multiplication relation. So that's the standard definition, is a so-called extended affine Hecke algebra of type A. But there is a so-called another presentation of this one. This presentation uses this identification, you see. But you have this isomorphism. So the next one is the so-called Bernstein, presentation. So we have the Hecke algebra. So I just modify the basis element. Then I introduce another generators called xj plus minus 1. So this Hecke algebra has generators, you see, the type A Hecke algebra part and plus this, corresponding to the weight lattice part. So there is the following presentation of this. So for TIs, you have this relation that defines type A Hecke algebra, and you have the other relations involving, the commutator relation between Ti and Xj. So this is a very standard way. So with this presentation, we define the action of Hecke algebra on the tensor space, on this one. So what do? So take a tensor, which is a basis element, you see, because this is an R-fold tensor product. So you take a tensor. Then you look at some fundamental region. So I introduce INR standard notation, where the components of I varies between 1 to the n. This part is used for the type A Hecke algebra definition. So here the VV's paper, they define the action. So this tensor space emits a right affine Hecke algebra module defined in the following way. First of all, you see, the xi defines just like the translation. You see, the xt minus is simply change the t's component, right, to it plus n. Others are unchanged. Then when I is in this region, fundamental region, then the action here is simply the type A Hecke algebra action. Then you use this translation. It defines uniquely an action of the whole affine Hecke algebra. Okay? So with this, well, in that you can prove, actually, in VV's proof, it's already mentioned because VV only mentioned the whole algebra action on this side, on the left-hand side. So affine Hecke algebra action on the right-hand side. And this action commutes with the Hecke algebra action. Sorry. This should be the double linear Hall algebra action. So this action commutes with double linear Hall algebra action. So then you got a bimodule structure. So let me move back here. So on the one hand, you have Hecke algebra action, affine Hecke algebra, and affine GRN. So you got a bimodule structure. Then you have two algebra homomorphisms. This time you take the endomorphism as the Hecke algebra module here, as a double linear Hall algebra module there. And so if both maps are surjective, then we obtain the so-called affine quantum Schur-Weyl duality. And now for KCR, there is probably a geometric proof around because Ginsburg, Vesserat mentioned that in their 1993 papers. And like Schiffman, in one of his survey articles, he mentioned, well, if you replace the SRN by GRN hat, then the onto map should be okay. But I say that a geometric proof is probably there, but we got an algebraic proof, or maybe combinatorial, because it's a conference workshop on combinatorial approaches. Okay, so what is the next one? So for this one, well, actually, it's natural to expect this is onto, but it's relatively hard to prove it. But one good news is Poulchen, has a proof at the specializations when V is the square root of Q, where Q is the prime powers. So this is a kind of geometric proof. But when you get a proof over prime powers, you cannot claim this is true over even this field of rational functions. So, but I believe something there, but we need a proof. And so then because of this, so this algebra here is called affine Schur algebra, quantum Schur algebra. So I should put affine here, affine quantum Schur algebras. Okay, so these are the two algebras which somewhat, on the one side it connects to the representation of Hecke algebra, on the other side it connects to the representation of affine quantum GRN. And so before I move on to look at the structure of quantum Schur algebras, affine quantum Schur algebras, so let's mention with VV's Hall algebra action. You see, the restriction of this double linear Hall algebra action, I should have action on this tensor space to the plus part. Plus part is actually linear Hall algebra, coincide with VV's Hall algebra action. Now, this VV's Hall algebra action defined use geometric approach, evaluations at certain filtrations of lattices, etc. But our action is just using the generators and the relations. So they are coincide. So the commutator formula actually derived from Schur-Weyl pairings implies following polynomial identity. So I want to mention, as I said, it's combinatorial, approach, right? So I want to mention this theorem. You see, you get to this kind of our action the same as the VV action. Then you look at VV action. Then you use this commutator formula coming from Schur-Weyl pairings. Then you will get to this kind of polynomial identity. So you see, I have two sequences. Now these are I use a triangle here means cyclic quavers. So these sequences are cyclic at period n. So that means you have lambda 1, lambda 2, lambda n. So that's a 1 to n position. Then you copy this part infinite many times. Then you get this set. Then you will see from this cyclic, two cyclic sequence, cyclic sequence, then you get these are Gaussian polynomials. Okay, Gaussian polynomials. Then you have polynomial identity. But it's interesting. We can't find a combinatorial proof. It's true, but we can't. But there's an interesting story about this formula because at the very beginning we use VV's approach. Then we look at double Hall algebra. Then when we want to get to the double Hall algebra action on the tensor space, we need these two must be the same. So we spend a long time trying to prove these two are the same in some way, but it turns out no way to get this done. Maybe we don't see a way. But anyway, then we change our approach. You see, we change the approach from VV's double action, double Hall algebra. We change it to the presentations we are talking about today. Then we define the double Hall algebra action on the tensor space. Then make a comparison with VV's action. Then eventually now you got this is proved. They're the same. They're the same from that approach. But the combinatorial proof is still quite unavailable right now. Anyway, so now this is a side trip. Now we move on to the quantum affine quantum Schur algebras. So I'm going to be move a little bit faster here. K is a field, any field. V is you see 3 modules of rank R. So this is standard definition for the geometric definition. This is the geometric approach too. So I get the geometric definition here, right? Well, people, many people talking about quantum affine Schur algebra use geometric definition. So this is one of them. So you take all filtrations of lattices, So that's a K epsilon lattices. So that's a polynomial lattices. And satisfying, of course, it's a filtration and the periodic conditions. So that's the set of all filtrations satisfying these two conditions. Then you start with the group of automorphism of this module. Then the group acts on the filtrations by component-wise. That's very standard. Then you will see there is a map. So from the set of filtration to these kind of cyclic infinite sequences. Okay, so you're just looking at the dimension as the K modules. So Li mod Li minus 1. Then this map induces a bijection, which is between the G orbits and the set. So what is this set? Well, this set I look at the cyclic infinite sequences, right? But this cyclic condition is given here, right? But the sum of the first R entries is R. Consecutive R entries is R. So that's the 1-1 correspondence. Now this is actually a finite set because your sequence are cyclic. One part is repeated infinite many times. So and your sum must be R, so it's finite set. Then on the other hand, the group acts on this kind of variety, F cross F with the diagonal action, and then it induces a bijection between the G orbits on this set and the set. Now this time I look at the infinite by infinite matrices with non-negative entries. They satisfy some cyclic conditions like this, and their sum. The first n row sum is R. Okay, so you add up to that. So of course, every row has a finite many non-zero entries if the sum has to be R. And so that set is infinite. That set is infinite. This is finite. This set is infinite. Okay, so because this bijection, the orbits corresponding to this matrix denoted by OA, right? Now with this OA, so you have labeled by matrices, so I can introduce an algebra. So to do that, you take A to be the finite field of Q elements, and then you look at, use F, span a free module, Z module, and the G acts on it, then take the endomorphism algebra and take the opposite. Then you can find a basis labeled by A, labeled by the orbits, right? And of course related to Q. And with multiplications, so you take EA times EA prime, and you get a linear combination. If the column A, row A prime, what does that mean? That means you take the column sums, form a vector. That's row A, you take a row sum, form another vector. If both are the same, given by this formula, otherwise it's 0. And what are the entries? The entries, you just take a fix, a pair of filtrations, right? Then this entry is just the number of L prime in F, such that L prime is in the orbits OA, L prime and double prime in the orbits OB. So that's very standard definition. I should say I use this definition, which is still relatively algebraic, but you can reinterpret this as convolution product, as the characteristic functions, whatever you want. Okay, and but the important is this coefficient is a polynomial in Q. That's important, and then you can define. You get kind of generic structure. So then I define this S triangle NR, that's the affine Q-Schur algebra, with basis EA, so I remove this little q, right? And the multiplication coefficients uses just the polynomial, otherwise 0. Then this is the associative algebra, because this is an associative algebra, and etc. So you have the anti-involution, algebra involution by transpose a matrix. So that's very much like the definition of the finite case, the quantum Schur algebra. That's exactly the same. Now, of course, there is some kind of a background of this kind of definition. If you look at Iwahori Matsumoto's earlier paper, for the affine Hecke algebra, used the periodic group definition and the Iwahori subgroups. So this is just coming from up there. But anyway, so this is kind of definition. So I said when we use convolution product in the above definition, then you can make the definition more geometric flavor. Okay, and you may interpret this definition above as, you see, I have already introduced the affine Hecke algebra. Then you take the trivial representation corresponding to the Young subgroup lambda. Then you induce up, take a direct sum, and endomorph them. So that's the same. And so what I want to say is, in VV's paper, there is Z algebra isomorphism from this kind of geometric definition and from the definition I gave before. Okay, and so I need some notations. So that's the affine Schur-Weyl algebra. So I need some notations to tell you some nice properties about this algebra. So first of all, these matrices with the sum of n rows to R, I take them union, right? Then I get a subset with diagonal entries are all zeros. So I use this set, okay? These are just periodic matrices with entries non-zero integers, and diagonal are zeros. Then I also use this basis EA, I defined in the previous slides, then modify with scalar. So I denote this basis by square brackets A. That's Bayes and Lutz-Macpherson notation. So then look, with this basis element, that's a basis for the Schur-Weyl algebra. Now, for every A in this set with diagonal entry 0 and every J, that's periodic sequences, okay? Then you define a sum of these square brackets A. So that's the way we do it, you see? I define AJR, which if the sum I mentioned before, the sum of the n rows, n consecutive rows, is less than or equal to R, I use this formula. That's a linear combination of the standard basis elements, but plus the diagonal of lambda, where lambda is taken from n R minus this value A. So you take with a scalar. So that's take a sum. This is the new basis in the finite case. Bayes and Lutz-Macpherson introduced this basis. And in the affine case, in VV's paper, they also mentioned this basis. Okay. Now, what I'm interested in is this will be a new basis, right? Well, here's the BRN type spanning set, because that's the quantum case, right? Now, look, I first state this. Well, look, the elements I define, I single out some, satisfy these conditions. Then I say this forms a basis. But that's not that important, actually. What is important is this set, when A varies, J varies, right, forms a spanning set for every R. For every R, you see? You just take A's, take J's, and R's. That's forming spanning set for every R. So this means somewhat this basis can be lifted as a basis for the quantum group when R is removed. Now that's a nice basis. I call it the BRM basis, because this is the basis can be lifted easily to the quantum GRN level basis. Okay? So, but before doing that, well, I mean lifted to quantum GRN, that's done, but affine quantum GRN, not yet, okay? But I will let you know. Now I introduce some notations, alpha I, beta I. Then I state a theorem, which is in the finite case, Bayes and Lutz-Macpherson discovered. You know, you have the arbitrary basis elements AJR. You have the generators, quantum group generators. Then you make the multiplication. You have explicit formula. For example, when this kind of general spanning set element or basis element, right? You multiply by this is zero matrix. This is like a product of KIs. Then you have this kind of relations. But more importantly, when you have this arbitrary basis element, then you have this, you see, E, that's corresponding to EH, right? The EHHI, that's the unit matrix, right? And then you make a multiplication, you have such explicit formula, such explicit formula. And that now we can generalize the formula to the affine case. And, but the one important thing is these coefficients, you see, when you look at these coefficients, well, they are all formulas are independent of R. You see, well, of course, these basic elements it depends on, but the coefficients independent of R. Now that's fairly important sign because you can lift up to get quantum group basis. If you see these structure constant or coefficients, right? They're nothing to do with R. And of course, I only mention one example. That's up triangular part. You can get the Fi, the Fi definition. However, the quantum affine GRN, the generators, there are other generators, central element generators, but we don't know the multiplication formula. We only get to the simple module. These are the simple module, the generators of quantum affine SRN. Okay, so to prove this surjective map, how many minutes I have? 10 minutes. I have to move a little bit fast. So now we discover some kind of a triangular relations. You see, you take a base matrix with diagonal zeros, then you look at the upper triangular part, lower triangular part, you make the product, then you will realize, well, you see this product has a term in the leading term, the other terms will be smaller. And for certain orders, which is generalized Brouillard ordering, okay, then this part can be rewritten as, because I have a basis or spanning set, right? So you can realize this the linear combination of the spanning elements. So therefore, in this Q-Schur algebra, that's the integral version. That's the over rational numbers, right? So you have this nice triangular relation. Now that's very useful, important relation. With this relation, I can further to construct a nice integral basis. So that's what I'm going to say. So I introduce some numbers I need for construct the compositions. But anyway, so the next result tells you, you see, if A is such a matrix, then I look at the upper triangular part, lower triangular part, then the zero part, that's a German K, right? Then I define lambda A, use this sigma I, I just defined the previous slides. Then you get some new elements, and the theorem is when you take P of A, where A varies from this index set, you get a basis. Now this is an integral basis over Laurent polynomials. That's a nice basis. At least when you try to study, the root of unity theory, I think this basis will play a role. But what do we need? If you want to look at, what do we need is from this basis, you have the triangular decomposition. So you have, this is the plus part spanned, this is zero part, is minus part. So for the affine Q-Schur algebra, you still have this kind of decomposition. Then, how do you get to the surjective map? Well, you just look at the whole algebra maps, positive part maps onto this, negative part maps onto this, zero maps onto this. So eventually you will get a surjective map easily from these triangular relations. So that's an algebraic proof. You get the double linear whole algebra maps onto the quantum affine Schur algebra. So that's the proof depends on the manipulation of Balians and Lutz McPherson type of basis, triangular relations. So here, okay, there are two comments actually. From here, as I mentioned that, because this quantum affine GRN is defined over rational function field, then how do you construct a Lutz type Z form? Well, there's a natural candidate, because I use double linear whole algebras. So I have the plus minus part of both integral linear whole algebras. Fine, no problem. And both are maps onto these two. Fine. And I have the zero part. Zero part I have also sort of integral version, like Lutzig's integral version. Then I put them three together to get a free Z module. Okay, this maps onto this integral affine Q-Schur algebra, but I don't know if this is a subalgebra. So we still don't yet know how to prove the three pieces together form a subalgebra, because the commutator relation derived from Schur-Weyl pairing is very complicated. So we still feel it's a bit harder to prove. The three pieces together it forms a subalgebra. If you get this subalgebra, that's definitely a nice root-stick type Z form, which can be used to study root of unity theory.
You mean that you don't know whether the commutation relation gives integral coefficient?
Yes, that's right, exactly. The commutator relations, you got the coefficients, and I don't know how to write these coefficients as root-stick, basis elements, the binomial, type elements. That's right, exactly. Yeah. So the second part. So this is one thing we don't yet solve it. The second part is, well, look, I want to get the Bailinson-Luther-McPherson type realization, hopefully. So what we are thinking about is, well, first of all, we modified Bailinson-Luther-McPherson's approach because in their paper they spend a lot of time to prove a stabilization property. This is not true in the affine case. We don't see anything like this. So what do? We just cut off their construction, throw away the negative part. We only look at the non-negative part. You see, I take a Z basis. So these A's involve matrices with non-negative entries. In original Bailinson-Luther-McPherson's construction, the diagonals are allowed to be negative. I don't do that. I consider all non-negative part. So in other words, I introduce a direct sum of all affine Q-Schur algebras. Then I take sort of a completion. So this is, I write down this just in a fashion like Bailinson-Luther-McPherson did. But actually, this is a product of the affine, Q-Schur algebra when R is any non-negative integer. So this is a kind of candidate, right? But we have already got a surjective map from quantum affine GRN to each of the components. So therefore, from here, sorry, I missed the equal here. I don't know why this is not there. But so I introduced certain elements. I defined AJI before. Now I take the sum, infinite sum. So this is an element in the in this direct product for affine Q-Schur algebras. Then you can prove, well, these elements is linear dependent. There is an equal here. This is linear dependent. So this spans a subspace. That's what I call the A triangle in. It's a subspace because it's spanned by A of J. So I throw away R's. It's spanned by A of J. Where A taken all matrices with diagonal zeros, J can be anything here. Okay? So that's the candidate of my realization. So anyway, I say this is the basis, first of all. This is the basis. Now that's called the Bailinson-Luther-McPherson type basis for this subspace. Okay, for this subspace. So I really want to know if this is the quantum affine GRN. Okay, in the finite case, yes, the answer is yes. In the finite case, in the affine case, the answer is not yet known. So, but anyway, we can state the following: the algebra epimorphism from double linear Hall algebra to affine Q-Schur algebra induces such a homomorphism, and you can prove easily this is injective. This morphism is injective. The question now, here is some interesting you observe. Restriction gives rise to the following algebra homomorphism. First of all, the image of this root-stick, quantum affine GRN maps into this subspace I mentioned. So the image is here. Secondly, the non-negative part all maps into this part. Okay? So it is, of course, natural you believe the whole image should be inside here, right? But we don't know, proof. So here's the conjecture. We believe the image is the whole subspace. So equivalently, this is the proof this subspace is a subalgebra. Now, this subspace is subalgebra. We don't know proof. I will explain why this is relatively hard to know this. Well, anyway, but this conjecture we checked when d equals 1 in the classical case, it's true. So that's a good sign. So why this is true? Let me explain why this is true. See, that's based on the following theorem. You see, when we look at affine Schur algebra, d equals 1, not the Q-Schur algebra, then you can find explicit multiplication formulas which that's the AJR, right? That's a version for the for the classical case. You see, this involves homogeneous, corresponding to homogeneous indecomposable modules. So that's H plus MM, where n is multiple of m. So these are the homogeneous indecomposable modules. And you have such explicit formula. Then you notice that all coefficients are independent of R. With this result, we can prove you got a subalgebra, because these are the generators. Now, these are generators of double Hall algebra, or the quantum affine GRN. So that's the point, as I said. That's a point we don't know how to get it down. You know, the V equals 1, we get such a formula. But for generic V, we don't know formula. So that's, anyway. So this is something we still work on. We hope we can do that. But anyway, it's not yet proved. Now, finally, in my last slide, I overused how many? Yeah, 1 minute. So now you specialize V squared to a non-root of 1. And then we consider algebra defined over C. Then we look at the representation theory. Now this part will be more interesting because for the affine Hecke algebra, the irreducibles are classified, etc., have nice property. So my first theorem says, well, when n greater than or equal to R, the category of the affine Schur-Weyl algebra modules is equivalent to the category of affine Hecke algebra modules. That's, so every talk should have a proof. So I have a proof here, very easy. So because n greater than or equal to R, this algebra is a centralized subalgebra. So like EAE, right? For some idempotent. Oh no, this is phi. I missed the H. This is phi H. Then we define the functor F, sending a module, affine Schur-Weyl algebra module to phi omega m. So that's natural functor. Then you define the inverse functor. The reverse functor is tensor product. Then you check gives the category equivalence. And a consequence from this isomorphism, every simple modules for the affine Schur-Weyl algebra is finite dimensional. That's very nice because this is the case for the affine Hecke algebra here. Of course, we can get that for the affine Schur-Weyl algebra, use this category equivalence. Of course, you will say, oh, you have restriction, but for n less than R, we can use some argument with Schur functors and etc. So that's all. And finally, of course, I mentioned something like a classification of finite dimensional simple modules. I know every simple module is finite dimensional. How do you classify them? And identification, because these modules are related to affine SRN, affine GRN. How do you identify these irreducible modules with the, we already know these modules, like given by Charlie Presley and other peoples. Okay? And Lutze's pi form, as I mentioned earlier, and the multiplication formula between these homogeneous indecomposable modules and the arbitrary basis elements, and etc., etc. So there are other more questions. These are most interesting questions. So I stop here.
Are there any questions?
What is the multiplication of the delta?